They're being ready.
Okay. All right. Welcome, everybody. How are you doing? Francis, Theophilus, James, Enoch, Princeton, Abraham, Armstrong, Harrison. It's good to see everybody. And as Harrison said, compliments of the seasons. I hope everybody's going to have a nice couple of weeks now with the holidays. And yeah, so this is our last meeting of the semester, as we talked about on the WhatsApp chat. So we're going to take a 1 month break and resume starting on Thursdays in late January, so on January 23rd. But I'll send follow-ups and I'll send more reminders about that. Um, so and as always, thank you as always for coming. And I've started the recording, so to get your record for attendance, please type your name into the chat, and it has to be typed in after the recording starts. Otherwise we lose it. Okay, so I'm going to mute everybody. Okay, and so in general, please only turn your microphone on if you want to say something or ask a question or answer a question, but otherwise we'll keep all of the microphones off. Okay.
Yeah,
Yes, Enoch.
good afternoon once again.
Good afternoon. How are you?
Yeah, so yeah, I'm okay. And good afternoon to my fellow comrades,
Hmm.
and good afternoon to our coordinators, good afternoon to our observers, good afternoon to everybody who has been in here from the beginning of the semester up to today, which we are about to.
Did you get did you lose your network?
Our
Sorry. Oh, there you
first
are.
day was,
You're there. Okay.
yeah, probably it was my network, so I want to firstly appreciate the
Not getting you.
people
Oh, there
and
we
the
are.
head.
Okay.
Yeah, sorry that someone calling me, someone was just calling me. So
Oh, okay.
I want
Okay.
to appreciate, yeah, I want to appreciate you a lot, especially, and those people who have been like standing by us, like reminding us every time to come online, taking our time to send us cards, spending our resources beyond us just for us to learn. I want to appreciate them a lot, and you too for the knowledge that you are imparting onto us. I really appreciate a lot that God Almighty will continue to strengthen you and give you more knowledge in teaching us always. So we actually got more to say. So due to time factor to the class, so I just zoom it, just pause it for now, and we'll continue. Maybe probably after the class we will talk more.
Okay. Thank you so much. Thank you. Okay, great. Um, okay, so I want to finish today with one of the big applications of calculus. We've done a lot of theory over the last couple of days. We talked about differentiability and second derivatives and formulas for taking derivatives and how to compute derivatives of certain functions. I want to make today a little bit more about real life problems and not only about mathematical symbols. So we're going to talk today about optimization, which is one of the very important applications of calculus. Okay, so we'll get to that when we get to it. But first, maybe we'll start by going over the homework. So I just want to review the rules that we talked about last time. So we talked about how to take derivatives of some functions that were not polynomials last time, right? And so we did two major theorems. So the first one was called the product rule, which said that if we have a function that is a product of two different functions, so h of x is f of x times g of x, and if f and g are both differentiable, meaning they have derivatives, you can take the derivatives, then the derivative of h of x is given by this pattern. I see that's an equals, and it should be a plus, not an equals. So h of x is f of x times g prime of x plus f prime of x g of x. So basic f times the derivative of g plus derivative of f times basic g, original g. Okay, and so this is maybe not the formula that you would first guess, but this is the formula that comes out when you try to actually evaluate this limit, evaluate this derivative based on its definition, based on the limit. So this here is the product rule. And then we have the quotient rule, which is the same thing, but for when you have a ratio of two functions instead of a product. So if you have f of x divided by g of x, then to take the derivative, you get this numerator that kind of looks like the product rule, although it's with a minus sign. So you have g of x times f prime of x minus f of x times g prime of x. And then this gets divided by g of x squared. So this is this extra term here that you don't have when you use the product rule. Okay, so it's just two different formulas, and both of these we could prove by, doing the limit, and the proof of the quotient rule was pretty tricky, but we did go through it. And then what we also did last time was we did some formulas for derivatives of trigonometry functions. So we saw that the derivative of sine of x is cosine of x, and the derivative of cosine of x is minus sine of x. And if you recall, there was a lot that went into this proof. We had to write down the limit for what this derivative means. We had to use the addition formulas for sine. And then we ended up having to evaluate these limits. Remember, we had to do the limit as h approaches 0 of sine of h over h, and also the limit as h approaches 0 of 1 minus cosine of h over h. So we had to do both of these, and these were not easy limits to do, right? I mean, in fact, we didn't even do the second one. We only had time to do the first one. But in order to do the first one, you had to draw a diagram and use a lot of right triangle trigonometry and then use this squeeze theorem. So again, I don't expect you to be able to just memorize this proof and tell it back to me, but I do want you to appreciate that there is a lot that goes into this proof. That the derivative of sine is cosine is not just, it's not clear, it's not obvious. It's not just, oh yeah, of course, the derivative of sine is cosine. There's really a lot of mathematics that goes into this very simple formula here. Okay. So, but now that we know that the derivative of sine is cosine, that's going to make that's going to be a very useful thing for us. Probably not so much today, but we'll see later on, especially if we talk about series, we'll see later on why this is so useful. So we talk about series in the spring. Okay. So this is the what we did last time, and this will get used a lot in the homework. So let's go over the homework question. So the first one is to try to develop formulas for the derivative of cotangent of x, which is the derivative of cotangent we saw as cosine of x divided by sine of x, and then also the derivative of secant of x, which is the derivative of 1 over cosine of x. Okay, and in both cases, well, we should just have this formula here. We're going to use this quotient rule formula in order to figure it out. Okay, so several people submitted correct solutions to this. So does anybody want to do maybe cotangent of x first to do this calculation with the quotient rule? So remember, with the quotient rule, we have to think of our function as being given by f over g. So we're going to think here of cosine of x is going to be our f of x, and sine of x is going to be our g of x. Let me rewrite the formula. The formula from the quotient rule is g of x times f prime of x minus f of x times g prime of x divided by g of x squared. Right, this is the formula for the quotient rule. I'm just copying it onto this page so that everybody can see it. Okay. So what what do we do? How should we plug this in order to calculate the final answer here?
Hello,
Hello,
hello.
yes. Yes.
Yeah,
You know.
yeah. So the first thing we do here, yeah. So the first thing we do here is that we see our f of x, which is in the numerator, there is cosine x,
Hmm.
and our g of x, which is in the denominator here, is sin x. So
Hmm.
now, by using the quotient rule, we know that we first have to differentiate f of x and whole g of x. So which means we have the derivative of cosine will be negative sine.
Right.
So
Great.
we write down, yeah, so we write down negative sine times pure pure or g of x. So which will be times sine x.
Great.
Okay, minus.
Hmm.
Yeah, and we know that the denominator, the derivative for it is positive cosine. So we have positive cosine times pure f for x, so which is cosine x times cosine x, all
Hmm.
divided by sine square x.
Hmm.
Yeah, so we will have sine x times negative sine x, we'll get negative sine square x
Right.
minus negative, okay, minus cosine square x.
Yep.
Yeah, so now okay, all divided by sine square x. We now
Hmm.
factor out negative 1 from up
Hmm.
there. Yeah, so if you factor out negative 1, so you will left with sine x plus cosine square x, all divided by sine square x.
Hmm.
And we know that sine square x, according to the Pythagorean theorem, we have sine square x plus cosine square x is equal to 1.
Yeah, so this is key observation. The most
Yeah, so
important trig identity that there is. Sine squared x plus cosine squared x equals 1.
yeah,
Yes,
so
keep
great.
going.
So
Yeah.
yeah, so you have negative 1 all divided by sine square x.
Hmm.
Yeah, so and we know that according to the inverse property, if you have 1 over sine x is
Hmm.
cosecant x. So if you have 1 over sine square x, it will be negative cosecant square x.
Great.
So that's it. That's the answer.
Great. That's absolutely perfect. Okay. It's to the pen stroke, exactly what I would do. So, yeah, so this is exactly what you get. So you get that the derivative of cotangent of x is negative cosecant squared of x. If you remember from what we did before, I'll just write it here. Well, maybe I'll write it back here. We also showed last time that the derivative of tangent of x was equal to secant squared of x. So cotangent of x is almost the same thing, but it's not cosecant squared of x, it's minus cosecant squared of x. The formula is just different. Okay? But this is what we get here. Yeah. So the derivative of cotangent of x is negative cosecant of x. And you get it by doing basically a straightforward application of the quotient rule. You just need to know what's your f and what's your g. And in this case, cosine of x is your f and sine of x is your g. All right. Any questions? Okay. So maybe let's do the other one. So let's do secant of x. So
Yeah,
similar thing, right? I'm still going to just label these as f and g, but it's going to
yeah.
be a little bit simpler. Yeah. Yeah. If you want to, Enoch, you can continue.
So we know that we are already getting the inverse property, and we know that f prime of x. Now we know that in the numerator we have 1, but the derivative of 1 will just be 0, which is a constant,
Hmm.
and the derivative for g of x, which is cosine x, it will be negative sine x. So at first we will have we have k. So just like that, tan 1 tan 0 minus 1 tan cosine x.
Right. Yes. Wait, no. G prime of, oh, sorry. I did this wrong. Sorry.
Yeah, so
The GX,
yeah,
this should be cosine of x. Sorry.
cosine x. Okay, so minus sin x.
Yeah.
Okay, so minus sin x.
Yeah.
Okay, so now we know that 0 times anything is just 0.
Well,
So
so
we
sorry,
will
wait,
have,
let's do the denominator also, just to get the full expression.
okay, so
So what do we have in the denominator?
yes, it will be cosine square x.
Great.
Cosine square x. So
Hmm.
we count down the 0 times cosine x is 0, and we just disregard that part. And we know that negative 1 times cosine x, it will just be that of positive sine x,
Hmm.
all divided by cosine square x.
Right.
And now we know that if we have a over b square, it can be written as 1 over 1 over a 1 over a plus b over a. So then that is
Times, right.
okay. So we will have 1 over cosine times sine over cosine. So we now know that 1 over cosine is secant. So
Hmm.
we have secant times tangent, the tangent function. So
Exactly, right.
if you like, you can arrange it. You can say secant times tangent. If you like, you can say tangent times secant.
Right. Either one is fine, right? So you can do secant x times tangent x or tangent x times secant x, or even, sine x over cosine squared x is not wrong. And it's not really that much harder than this form. But most people use this later form. It's a little bit easier to remember. Turns out to be more useful for integration problems later on. So usually I would say remember this, that the derivative of secant x is secant of x tangent of x. Okay? Or tangent of x secant of x, which is the same thing. And I should just say we won't do this all out, but I'll just give you a fact just so we can finish up the rest of the trigonometry functions. The derivative of cosecant x turns out to be negative cosecant x cotangent of x. Okay? This is also an exercise. You just do the same exercise, but use 1 over sine instead of 1 over cosine. Otherwise, you do
Yeah,
it the same way.
the,
Uh,
that was.
yes, yeah.
Yeah, the exercise on finding the derivative of x raised to the power n. I sent it. You saw it.
Yes, yes, I saw that. Yeah, I responded.
Okay.
Okay, yeah, that was all fine. Okay. So, okay, good. So this is how we calculate the derivatives of the other trigonometry functions. Once you know that sine gives cosine and cosine gives minus sine, then you can get everything else by using the quotient rule. Okay, so in particular, the derivative of cotangent is negative cosecant squared. The derivative of secant is secant x tangent x, and the derivative of cosecant is negative cosecant x cotangent x. And as you see
Yes,
these over and over, you will memorize them. Yes, Princeton.
that are always so is you are trying to tell us the derivative of cosine is negative sine as well?
Yes, this is what we saw yesterday.
Okay. So do you
We
want me to
didn't prove
okay.
this. All that we only
Yeah,
proved that
yeah,
the
I
derivative of
understand.
sine
I
is
understand.
cosine, and then I said you can do something similar, and that will prove this other formula. But we didn't do the details of this. I just stated it at the end of last class.
Okay.
And we're not
Thank
going
you.
to do the details. Okay, you're welcome. Other questions? Okay, let's go on to number two. So this is ask you to differentiate this function that I just wrote down. And one thing to keep in mind here is that this is what's sometimes called a compound differentiation problem. And when you see these, I didn't really tell you about strategy, but the idea is you want to look at what is the big structure of this function, right? And the big structure of this function is that it is a fraction, right? We have a numerator that we'll call f, and we have a denominator here that we're going to call g, or f of x and g of
Yeah.
x.
Hello.
Yes, hello?
That was.
Yeah,
Yeah. In the numerator we have f of x times g of x. Then in the denominator is h of x.
right. So exactly. So in the numerator, this is why it's compound, right? It's a fraction, but this part over here, when we have to differentiate it as part of the quotient rule, this will
Okay.
require the product rule. Okay, so this will require the product rule. Okay, so what we do is we start this out with a quotient rule, right? Which is going to be our usual formula, g of x, f prime of x minus f of x, g prime of x divided by g of x squared. But after we do this, this requires doing the derivative of this numerator, which is x sine of x. And so when we evaluate this part of the term, we're going to have to use a product rule to do it. So there's going to be basically two steps to doing this problem, right? So we are going to start with with using the quotient rule, right? So g of x here, right? This is 3x plus 4. And then the f prime of x, I'm not going to do yet. I'm just going to write it as x sine x prime, right? So we're going to have to take a derivative of it, but that will use the product rule. So let's not do that yet. Let's just leave it as one thing. This here, right, this is g of x. This here is f prime of x. And then the rest is straightforward. Minus f of x, which is x sine of x, times g prime of x, which is just 3, right? This here is f of x. this is g prime of x. And then in the denominator, we have just g of x squared, so 3x plus 4 squared. In general, I'm not going to simplify any of these terms. We'll just leave it as it is. Okay, and so now the only thing we have to do is now we have to do x times sine of x prime. We have to do the derivative of this. So how do we do that?
Yeah.
Yep. Mm-hmm.
Yeah, so now over there, we are going to use the product rule where we get the function inside f of x. So we have x as a function on its own, and we have sin x as a function on its own. So the derivative of x will just be 1 times sin x. So you will have, first of all, you are going to write down g of x pure.
Mm-hmm.
So you will have, you will have x times sin x, then plus
Was there not x times sine x? You have
x times x.
one times sine x.
Okay, yeah, one times sine x plus cosine x times x.
Right, because we have the derivative of the x times the sine x, that's 1 times sine x, plus the pure x times the derivative of sine x, which is cosine. So 1 times sine x plus cosine x. Great, so now all we have to do is substitute this in, and so we end up with 3x plus 4 times, I'll write it as sine x plus x cosine of x, and then minus, I'll just combine this all as one term, 3x sine of x, and then divide it by 3x plus 4 squared. And I won't simplify anything. You could simplify this if you want to, but it's not like this function is that important. It's more just to get practice using the rules. So once you get it into this form, 1 second, Enoch. So once you get it into this form, then I'm happy to just leave it like this. It doesn't need to be simplified. Yes, Enoch?
Yeah, hello. Yeah, what if I decide in my solution to distribute these two products, the 3x plus 4, and then there's one to distribute and simplify my answer for them. Will I still be correct?
Yeah, you'd still be correct. And in fact, you'd get a term of cancellation, so that's kind of nice.
Yeah, sure.
But it's not necessary.
Okay.
Okay.
Thank you.
You're welcome. Okay. Other questions?
Yes, Dr. Ogus, Christian?
Yes, Princeton.
Yes, where we have the S sine of S prime, and then we can down get 1 times sine of S plus cosine S times S. I don't know. Is it a formula that was derived, or it's
No,
it's coming from the prime?
This is coming from the product rule.
Okay.
Right. So remember because this is a product, right? This is x times sine of x. So in order to use the product rule, the x becomes a 1. The sine of x stays sine of x, right? We take the derivative of the first times pure the second. So that's 1 times sine of x. And then we add pure the first times the derivative of the second. So that's x times cosine of x, right? Remember, this is how the product rule works. So when we have this prime just means take the derivative. So when we take the derivative of all of this, we get sine of x plus x cosine of x. And so that means into this formula here, where we have x sine of x prime, the derivative, instead we write that as sine of x plus x cosine of x. The rest of the expression remains the same. We're just evaluating this piece that we have to use the product rule to evaluate. Is that okay?
Yes.
Okay, good. Okay. All right. Any other questions? Okay, so let's do the third homework exercise. So suppose f and g are two functions. I'm not going to tell you what they are. Oh, yes, Rash, question.
Hello?
Hello, Rash.
Yeah, I come on. Go.
Yep, coming on.
No, is this so because my network is giving problems, so I don't know. Is exercise number 2, right?
Yeah.
Is also right? Okay, okay. Okay. Thank you.
Okay. Oh, you're welcome. Okay.
Right.
All right. So we're now going to do exercise 3, which is the last exercise before we start the new stuff. Okay. So suppose f and g are two functions that are differentiable at x equals 5. So I'm not telling you what the functions are. I'm just going to tell you that they have derivatives at x equals 5, and that this is, I'm going to give you a little bit of information. I'm going to say f of 5 is 1, f prime of 5 is 6, g of 5 is minus 3, and g prime of 5 is 2. Okay. So now the question is, can you calculate the derivatives of f times g and f divided by g at x equals 5 from just this information that I've told you? Okay, so no, I'm not telling you what the functions actually are, but I'm telling you enough information to do this. Okay, so I'm going to write this here. We're going to have d dx of f of x and g of x. And this will all be, this is the notation at x equals 5. And then over here we have d dx of f of x divided by g of x. And this is again here at x equals 5, right? So was there a comment? Was there a comment?
Yeah,
Yes, Enoch?
yeah. Can I give a comment on the solution steps?
Sure.
Okay. So first of all, we can take the general function to be like h of x to be equal to, yeah. So we can take the h of x to be equal to the function now. So if you are taking h of 5, okay. So if you are taking h of 5 now, we know that
h prime of 5, right?
Okay, h prime of 5, and we know that the function here is in the product form. So we have f prime of x times g of x plus, okay, so plus g prime of 5 times f of 5.
Right. So this is just the product rule. Let me just interrupt for a second. This is just for everybody else. So this is the product rule. The product rule lets you take the derivative of a function, but you can always plug in a value, right? And the product rule still works. So this is saying if you plug in 5 for the function, then when you use the product rule and plug in 5, this is what you get. You get f instead of f prime of x, g of x plus g prime of x, f of x. We get f prime of 5, g of 5 plus g prime of 5, f of 5.
Okay.
Okay. Continue.
So I should continue? I should continue?
Yep.
Yeah, so now we here now it's just basic algebra. Now you just insert the values where you have f prime of 5 is equal to 6, and we have g of 5. Our g of 5 here is -3, and we have plus our g prime of 5 here is 2, and our f of 5 here is 1. So now we will have -18 plus 2.
Great.
Yeah, so we will have -16 to be h prime of 5.
Excellent. Yeah, so that's exactly right. So h prime of 5 is -16, and you just use the formula. And because we know what all of these values are, we can get an answer even without knowing the functions f and g. All that matters is what is their behavior at 5. Okay? And knowing the values and the derivatives at 5 is good enough to is good enough to get the entire thing. Okay. All right. So thanks, Enoch. So Prince, I see an answer here, which I presume is for the other example. So for f of x divided by g of x. So Prince, do you want to do? Well, Prince, would you like to demonstrate this one? Or is your network not good? Okay, network not good?
Yeah.
Okay. Oh wait, sorry, I heard something. Or Enoch, is that just in the background for you?
Oh, okay, so
okay,
I should continue?
you can do this example. Okay, I think Prince is not answering, so you can do this example.
Okay, now so we know that our general function here is h of x, and we will have h prime of 5 to be, okay, h prime of 5 is equal to f prime of x times p of g of x.
Yeah.
F prime of x times p of g of x or g of 5.
Right.
Yeah, so minus, yeah, g prime of 5 times pure f of 5. All divided by g square of 5.
Yeah. The network giving us problem, already, Yeah.
Okay.
Yeah.
Okay. Hopefully, at least in the recording, or hopefully you can
Yeah.
hear now, even if it's hard to participate. Sorry about that.
Hello?
Okay. Yeah. Yes, Rash?
Yeah, I was talking about like the network giving me hard time. That's the reason I wanted to come in. But no problem, I could go ahead.
Okay, good. Sorry. I'm sorry that's happening.
I'm good.
Okay. Enoch, do you want to continue the example?
Yeah, so yeah, and we also know that our f prime of 5 here is 6, and our g of 5 here is -3. And so we do 6 times -3 minus our g prime of 5 here is 2 times our f of 5 here is 1, all divided by g of 5 square, which our g of 5 is -3. -3 all square. So now we have 6 times -3 will be -18 minus 2. So all over 9, all over positive 9, because a negative square is positive 9, is equal to -20 or divided by 9.
All right.
So the
Perfect.
function is -20.
Okay, perfect. And we'll leave the answer like that. And so, Prince, that your answer was correct. And hopefully everybody else was able to hear how we do the problem, right? So, these problems are not that hard, right? You have two rules and you just have to apply them. And you just have to know which functions you're using. What is your f and what is your g? And then you just apply the rule. And if it's asking you about a specific value, like x equals 5, instead of the entire function, then you just punch in that value into the formulas. Okay, so using the product rule and the quotient rule isn't that hard. The only harder thing is to just learn this rule, which is a little bit complicated. But if you do a few examples, and you can always do more examples from the textbook if you want to, then the formula will start to get memorized pretty easily. Okay, so these are a couple of exercises, but you can always do more. And once you know the formula, it's not that difficult to apply. Okay, so any questions about either of these exercises?
So, hello?
Yes, hello, Rash.
Exercise number 1. Can I see it because I tried getting there around? I was like, yeah, okay. All right. I see it. Thank you.
Okay, you're welcome. Other questions? Okay, so let's move on to the new material for today. So today we're going to be talking about optimization, which is a very important application of differential calculus. And so this asks the basic question, how do we find the maximum and minimum values of a function on some interval? Right? So you can ask this as a purely mathematical question, like here's a function, here's an interval, find the maximum and the minimum values. But where this really gets its power is when you try to model some real life situation with a function, and you're then actually able to optimize something in real life. So this can be used to model many kinds of applications. So for instance, what is the most economical shape to create packaging for a product in? So there's an example in the book that we're not going to do, but you want to design a can that's going to hold a certain amount of liquid, and you want to know what is the least material you can use to design the can in order to make it hold the most volume of liquid. So that's a maximizing and minimizing problem that calculus will be helpful for. If you're plotting a space shuttle mission, you might want to know what's the maximum acceleration of the rocket. That's going to matter because your astronauts inside can maybe only withstand a certain amount of acceleration. Otherwise, it's harmful to the body. How much of a product should be manufactured to minimize the average cost of manufacturing? So, for instance, usually it costs a lot to just manufacture a small amount of product, but the more you do, you get what's called economies of scale, and your average cost goes down. But if you want to do too much, then the economies of scale stop working, and then it costs more. So this is a question. How much should be manufactured if you want to minimize the average cost of manufacturing this? And then something for agriculture. So what's the largest area that can be fenced in by a certain amount of fence? Or for instance, if you have a certain amount of fencing, so you have a certain amount of fencing, what is the largest area that you can fence with that? Okay. So all of these are examples of what are called optimization problems. You're trying to maximize something or you're trying to minimize something. Okay. And there's lots of other applications. Also, you can see a few of them in the book. So what we're going to do today is we're going to start with just doing optimization problems in the abstract, so just in the context of math. And then we'll set up some word problems and some applications involving how to do these optimizations. And the idea is that everything is going to be based on calculus. So we haven't yet said how this is related to calculus, but calculus and derivatives are going to be what's going to actually help us do this. Okay? So let's talk about, so first we need to set up some definitions. So let's suppose that we have a function that's defined on a certain domain D, okay? So we have these 4 different definitions. Looks like a lot of symbols, but they're all kind of the same definition. And I'm going to draw a picture on the next page so that we can see what these things really mean. So all of these definitions start the same way. If we have a point in the domain of the function, so something that we can plug into the function, some number c, well then f of c, we call it an absolute maximum. Sometimes instead of absolute, people also use the word global. So an absolute or global maximum of f on d, if what? It means that f of c is bigger than or equal to f of x for all x in d. So everything in the domain, when you plug it into f, you never get as big a value as you get when you plug c in, right? So plugging c in gives you the maximum possible value for f anywhere on the domain. Definition for an absolute minimum is exactly the same. If c is in your domain, then f of c is an absolute minimum of f on d if f of c is less than or equal to f of x for all x in d. Okay? So what that means is whatever value you get for f of c is going to be less than or equal to the value you get for plugging in anything else. Okay, so punching in C gives you something smaller than punching in anything else. That's what's called an absolute minimum. Okay, so now we have the other versions of this. So these are called local, but they're also sometimes called relative. So I'll use that word also. So absolute and global are sometimes interchanged, and local and relative are sometimes interchanged. So the definition starts the same way. So if C is in the domain, then f of C is a local maximum of f on D. Well, it looks almost the same if f of C is bigger than or equal to f of x. So if it's the biggest, but now we're not asking to have this inequality on the entire domain. We're just asking to have this inequality in some interval around C. So for all x near C, okay? So it's not saying it has to be the biggest on the whole domain. It's just saying that it has to be the biggest in its immediate area, in its immediate interval. So imagine like a mountain. I mean, I'll draw this on the next page, but imagine a mountain that's not the tallest mountain in the country, but it is the tallest mountain in its area, right? So that would be kind of like a local maximum, even though it's not an absolute maximum. Okay. So the peak of that mountain would be a local maximum. And then we have the same definition for minimum. If we have something in the domain, then f of c is a local minimum of f if f of c is less than f of x, maybe not for everything in the domain, but at least for all values that are near c. So it's lower than everything else near it. And sometimes we use this word extremum This is just a generic word that means either maximum or minimum. So to say that you have a local extremum means that you have either a local maximum or a local minimum. To say that you have an absolute extremum means you have either an absolute maximum or an absolute minimum. And I guess I should just make a remark about language if you haven't seen this so much. The plural forms of all this are maxima, minima, and extrema. So they use the Latin form. Do this. Okay. So we talk about absolute maxima, absolute minima, and local and absolute extrema. Okay. So sometimes it's hard to really understand what's going on just from seeing a technical definition. So I just want to draw a picture and label things, and I think that should make it much clearer. So let's say that we have the graph of f of x. I'm not even going to give you the function, so let's just say we have y equals f of x here, and I'm going to draw the following function. Okay. So in this case, so this is our x value and this is our y value. So if we want the absolute extrema over here, this point right here, let me just draw it as a point. So this point right here is clearly the smallest value of the function, right? So this would be the absolute minimum. This point over here, certainly the largest y value of the function. So this would be the absolute maximum. And now this point over here, well, it's not the absolute minimum because it's bigger than this value here, but it is the local minimum, right? Because it's smaller than everything that's close to it. It's locally, it's the lowest point. You have to get much further away up a hill and down a valley to get to something that's lower than that. So over here is not the absolute minimum, but this is a local minimum. And then
local.
similarly,
Yes.
yes, you know.
Yeah, so which one you can also refer to as relative maximum?
Right, yeah. So this is local is the same as relative, and absolute is the same as global. So you'll see both words.
It's the same thing. It's the same thing I was thinking because it's sometimes called a local minimum or a relative minimum.
Yeah, same thing.
Okay.
And here, what you have is a local maximum, right? This point here, it's not the highest point on the graph. That's this one, but it is the highest point in its area, right? Everything that's immediately next to it is going to be lower. Okay, so we have... Yes, Princeton.
So this one can be presented in this subject. Besides the using calculus, it can be presented in physics or in geography.
Yeah, exactly. So you can think of it as geography, right? I mean, it's one-dimensional geography, so it's not exactly realistic. Yeah. But you can, I mean, you can do this in 2 dimensions, and then it is actually geography. But you should think of this as a valley. So a local minimum is kind of the floor of any valley. The absolute minimum is the floor of the lowest valley. But any valley floor gives you a local minimum. And same thing with a mountaintop, right? The absolute maximum is the top of the highest mountain. The local maximum is the top of any mountain or any hill, right? That's going to give you a local maximum. Okay. So does this, we're not going to do any math on this page. It's just so that you can see the picture. So does this picture make sense for the intuition of what's an absolute maximum and minimum and what's a local maximum and minimum?
Okay. Hello.
Hello. Yeah. You know.
Yeah. Depending on this minimum and maximum values of the functions, I want to know. I want to know if the graph of both, if you got a function y is equal to sin x, and if you got the inverse of that function, which is cosine x, if you have those 2 graphs on the same plane, or they are plotted together on the same graph, would they have local maximum and local minimum, or would they have only absolute maximum and absolute minimum?
Okay, so actually we're going to do cosine of x. We're going to do sine of x on the next page.
Oh wow,
But but
even there, wow.
maybe let me just say something though about your question. An absolute maximum is also a relative is also a local maximum. So this is also a local maximum, right? So
Yeah,
this is
yeah,
it is
because
bigger than everything near it. So it's a local.
yeah,
So every absolute maximum is also a local maximum, but not every local maximum is the absolute maximum, right?
okay, so
So
because the reason I'm asking, I've been doing some graph. Basically, like, I just have like or four rise and four, rise and four, rise and four. It doesn't have any middle effect like to have
right.
local maximum, yeah, and relative thing like that.
Okay, yeah, we'll do this on the next page. Okay. But before we do that, any further questions about this graph?
So that August.
Yes, Princeton.
So I mean, using this guy, it has a static position and any position.
Mm-hmm. Sorry, I didn't get the question.
Using this graph, do we have a static position in any position?
So using this graph, we have the
Where there is a static position by static, and then going to any position.
okay, the position, yeah. Um, yeah, I'm sorry.
Do
I
we
think
have beginning of it? Do we have a beginning of it
do we have
for the graph?
an
Yeah,
expression? No, no. I
it
just
just
drew a graph.
okay.
Yeah, I didn't give you an equation or anything like that. I'm just drawing a graph to represent visually what these things look like. No, I haven't told you an
Okay.
equation for this. Yeah. Okay.
So a graph can. So I want to ask whether a graph can start with a local mass and then go up to a global mass. Can it start also like that?
Yeah, I mean, we have a local max and this is the global max, right? They're just two different. We have several local maxes, right? So these are both local
Okay.
maxes, and this is the global max here.
Yeah, that
So
was
yes, you know.
yeah. Or actually, the question he's asking is trying to say if can a particular graph start exactly at a
Oh,
local
okay. Can
maximum?
it start? Yeah, absolutely. Sure.
Yes,
Yeah.
yes,
Yes.
yes.
Sorry,
That's the
sorry,
question
sorry.
I'm asking.
I didn't get you so clearly. Yes, yes, yes. I'll show an
Okay.
example of that.
Okay, thank you.
Okay, you're welcome. My apologies. Okay, I will show an example of that.
Mhm.
Okay, so let's do this example then on the next page. So we have the absolute and local maxima and minima for the following two functions
Yeah.
defined
So
on
yeah,
R. Sorry, Enoch,
yeah. So this
sorry, do you have a question? Yeah.
yeah, this is the same thing I was saying. Now you will see the behavior of the graph of sin x. It will be kind of a contradicting form, and the behavior of the graph of x square, it will open upward. Yeah. So
Right.
now,
So
okay. So
let's draw these graphs. So
Yeah, I
sine
see.
x looks like this.
yeah, I think the graph of x square you have to address it on the other side small.
Yeah.
Okay.
And here.
So it will open upward in respect to the positive value. Yeah.
Okay. So we're trying to find everything on these. And so what we see from sine of x, what are the local maxima? The local maxima are the same thing as the absolute maxima, right? Because the highest value is 1, right? So this is both
Yeah,
the local and absolute maxes. Every point at the top of a sine wave here is both the local maximum and an absolute maximum. And there's nothing else. And likewise, we have local and absolute minima. That's every bottom of the wave is going to be a local and an absolute minimum. Okay, whenever we hit -1 over here. Okay. Okay, so sine just has lots and lots of local maxes and lots of absolute maxes and lots of local minima and lots of absolute minima. Okay,
Yeah.
so this
yeah.
here is
My
y equals sine
my
x.
question here.
Yes, question.
Yeah.
Yes,
So
Princeton.
if the point hits the vertical mass, will it still be the sign of X?
If the point hits the vertical line,
Yeah, as you can
what
see.
vertical line? You mean the y-axis?
Yeah. What?
Okay. So this point here, I mean, this is y equals sine of x. On the y-axis, it passes through the point 0, 0, right? This is just a point in the middle. It is not a maximum and it's not a minimum of either kind.
Meaning you join the curve, and then the curve point hits the y-axis. This is what I'm asking.
Right. So I'm drawing the curve. The curve hits the y-axis
Yeah,
here.
yeah.
Yeah.
Going up into that direction.
Yeah, it's going to hit the y-axis here. But that's in the middle of the wave, so it's not going to be either maximum or minimum. Okay. Now over here, we have y equals x squared, and we have a point over here. This bottom one here is both a local and an absolute minimum. And what about maximum? Well, there isn't any, right? There's no local maximum on this graph, right? There's no point here that's bigger than all of the other points around it. And there's no absolute maximum either because these values go up to infinity. So this graph has no local or absolute maxima.
Yeah, so it was the same thing I was saying based on the behavior of different graphs.
Yeah.
Even yeah, even like if you see like the graph of SQ, or if
Mm-hmm.
you see the graph of L raised to the power of 3/2, if you see the graph of secant X, if you see the graph of like cosecant X, all those
Mm-hmm.
things they behave different ways.
Yeah. Exactly. So they all behave different ways depending on what your exponent is there. And what I should say is even the same graph can behave a different way if we restrict the domain. So let's say that if we restrict the domain to, let's say, the closed interval from -1 to 1. So let's say that I have this is -1 and this is 1. And let's say that I restrict the domain so that the graph of the function isn't the whole parabola, but it's only this segment of the parabola from -1 to 1. Then what happens over here? Oh, I see. Yes. Oh, sorry. Princeton. Yes. Sorry. The graph that you've drawn, this is the cosine graph. So for cosine, you would have the absolute maximum on the axis. Yes, that's right. But we're doing sine instead of cosine. Yeah. So that's the crest hits the y-axis. That's in cosine, and that would be the absolute maximum. But that would be for cosine graph, not for sine graph.
Okay, thank you.
Okay. You're welcome. Okay. So in this green graph, if I restrict the domain to just -1 to 1, then on this green graph, now these endpoints are both absolute and local maximum. And so this point over here is also an absolute and a local maximum. Because remember, a function is not just a rule. A function is a rule and a domain. So saying that I'm going to take the domain to be -1 to 1, that is a different domain than what we start with. Okay. And when I change the domain, even though it's the same rule, I change the properties of the function. So if my graph is only the green graph, because I'm saying the domain is only from -1 to 1, then all of a sudden I do have maximum values on the opposite endpoints here. Right? I've got these maximum values. Whereas if I take the domain to be all the real numbers, the whole number line, then I don't have maximum values anymore. Right? Then the graph will just go on forever and there's no local maximum and there's no global maximum. Okay. Questions on either of these? Okay. So now let's talk about, so far we haven't done any calculus, right? We've just been drawing graphs and looking at them. So let's do some calculus now. So actually, yeah, so here's where we're going to have our first things. So we have a couple of theorems about extrema. So there's two major theorems that we're going to use about local and absolute extrema. And they're pretty intuitively clear when you look at the graphs, although to actually do a serious proof of them is not so easy. It's in part of what you would call real analysis or mathematical analysis to do this kind of proof. So we're going to skip the proofs, but you can read one of the proofs in chapter 3.1, 148 of the book. In fact, everything from today is from chapters 3.1 and 3.5 in the book. Okay? So the first theorem is what we have over here. So it says if a continuous function f is defined on a closed interval from a to b, so this is very important that it's defined on a closed interval, then f attains an absolute maximum and an absolute minimum somewhere on the interval. So if we have a closed interval, we're guaranteed an absolute maximum and an absolute minimum, right? So for instance, if we go back to our example here, right, this parabola originally is defined on the entire real line. That's not a closed interval. And in fact, it does not have an absolute maximum. It has a minimum, but it doesn't have a maximum. But if we change the domain of definition to be a closed interval, like -1 to 1, it becomes this closed interval. Now this graph does have a local minimum and a local maximum, and it does have an absolute minimum and an absolute maximum, right? The absolute minimum is just here, and now it's got absolute maxima right here at the endpoints of the interval. Okay. So if you're on a closed interval, you're guaranteed to have a maximum and a minimum. Okay, on something on an open interval or on something like the whole real numbers, then you're not necessarily guaranteed, as we see from this example. Okay, so the first theorem says that if you're defined on a closed interval, then you're guaranteed to have an absolute minimum and an absolute maximum somewhere on the interval. Okay. The second theorem, which we will let me say this. I want to. So the second theorem is going to be if you have a local maximum or minimum at a point C in, I should say, in the interior of its domain. So not at an endpoint. So in the interior of its domain. And if you can take the derivative there, then the derivative is always 0. So if you've got a function that's differentiable at a point, and that point is a local maximum or minimum, then you're guaranteed that the derivative there is 0. And this is also something that we can basically see from the graphs. Let's look back here at this sine graph. We have all of these local maxima, and we have all of these local minima. And what you see here is when you try and draw the tangent line, that all of these tangent lines here are horizontal, right? They all have slope 0. And that's what the theorem is saying. It's saying that if you are a local maximum or local minimum, then the slope of the tangent line there has to be 0. You can't be in the middle here, which would be a positive slope of the tangent line, because that basically means there's stuff below you and there's stuff above you. You're not going to be a local minimum or maximum. But when you're a local maximum, what happens basically is that the graph goes up to you and then it goes back down. And at the point where you have your local maximum, if you have a tangent line, if you're smooth, then you have a horizontal tangent line. And same thing for a local minimum. The graph goes down and then up. And at your local minimum, you're going to have a horizontal tangent line. And remember that the derivative, what does the derivative mean? It's easy to get so wrapped up in the formulas for computing the derivative that you forget what the derivative actually means. Why are you computing derivatives? What the derivative means is it's the slope of the tangent line. So having derivative equals 0 is the same thing as saying the slope of the tangent line is 0. And that's saying that your tangent line is horizontal, right? That's what slope 0 means, is that it's horizontal. And you see from this graph, when you reach peaks and when you reach valleys, the tangent line is always horizontal. That's the content of this other theorem. Okay? So going back, we have these two theorems. If you're continuous on a closed interval, you always have an absolute maximum and an absolute minimum. And then if you have a local maximum or minimum and you have a derivative, then the derivative has to be equal to 0. Okay? And one quick warning here, you can have the derivative be 0 without there being a local maximum and minimum. And so the classic example of this is if you take x cubed at x equals 0, then if you draw the graph, it looks kind of like this. This is the graph of y equals x cubed. And over here, you do have a horizontal tangent line at the origin, but it's not a local maximum or minimum. So that's okay. It's the statement works in the other direction, says if you have a local maximum or minimum, then the derivative is 0. It does not say if the derivative is 0, then you have a local maximum or minimum. Those two statements are the logical converses of each other, and they're not the same statement. Okay? So if you've got a local maximum or a minimum and you have a derivative, then the derivative has to be 0. But if the derivative is 0, maybe there's a local maximum or minimum, but you don't know. The theorem doesn't guarantee you that. Okay. So these are the theorems that we're going to use when we do actual optimization problems, which is what we're going to do for most of the rest of class. And they're both kind of things that you can see. You know, you've got a continuous function on a closed interval. Of course, somewhere it's going to take its maximum and somewhere it's going to take its minimum. It can't go off to infinity. It's on a closed interval. But actually proving this is pretty hard. And then does it have a local maximum or minimum at a point C in the domain? Then you're guaranteed that if there's a tangent line, it's got to be a horizontal tangent line, just like what we see here on this graph. Okay. I see I'm doing Christmas colors over here, so this is good for this week. Okay, so any questions about these two theorems? So we can already kind of see how this is going to help us when we do problems. We're going to be trying to find maximum and minimum values, and one thing that we can do is check to see when the derivative is 0, and those are going to be the potential maximum and minimum values. So this is how calculus is going to come in, how it's going to help us, right? This is the first calculus of the day, right? This f prime of c equals 0. Okay, but it's going to turn out to be,
Yes,
it looks very simple, but it's going to turn out to be very important. Yes, Princeton?
yes. Do we have a fixed interval for theory one?
A fixed interval
Like,
for theorem one,
yes,
any
yes.
closed interval.
Okay,
This works for any closed interval.
okay.
Yeah. Okay. So let me just do one more consequences, and then we'll get to actual problems. Okay. So consequence of the theorems is, so first just a definition. If we're in the domain of a function, then we call C a critical point, or sometimes some books will call it a critical number. Same thing as a critical point. If either f prime of c is equal to 0 or f prime of c does not exist, right? So it might be non-differentiable. Remember, we've seen things can be non-differentiable because they have corners, or because they're discontinuous, or because they have vertical tangents, right? There's lots of reasons that something can have a derivative that doesn't exist. And so the corollary of the theorem says, if you have a local extremum, well, we know that if you're differentiable, the derivative is 0. Maybe you're not differentiable. That's fine. But what this is saying is that if you're a continuous function with a local extremum at C, then this C is a critical number for f. So the only places you can find local extrema are going to be at critical numbers. Okay? So you only have to check where the derivative is 0 or where the derivative doesn't exist. And the second corollary is that if f is defined on a closed interval, and if we have an absolute extremum, then either c is a critical number or c is an endpoint. So let me say actually what's going on here, right? If we have absolute max or min is either occurs at a local max or min in the interior, this would be the critical number case. because local maxes or mins come from critical numbers, or occurs at an endpoint. Okay? And these are the two cases. And so this is how we're going to do max-min problems. We're either going to, if we want to find the absolute maximums or minimums of some function on a closed interval, they're either going to occur at a critical number, so at a place where the derivative is 0 or doesn't exist. Those are the only places where you can have something local. Or maybe they're going to happen at the endpoints also. So we've got to check the endpoints of the interval. Endpoint just meaning A or B. Right? Those are the endpoints of the closed interval A to B. Okay? So this is the theory. Now we're going to do some problems. How do we do these problems? Well, we have to have a function that we're trying to maximize or minimize. We want to find the absolute maxima or minima on some closed interval. And we're going to have to check, find all of the critical numbers, and find the endpoints, and see which of these gives the biggest value and which of these gives the smallest value. Okay? So for instance, let's look at this example. So algebraic example. So find the absolute maximum and minimum for the function f of x equals 2x cubed minus 3x squared minus 12x plus 1 on this interval from minus 2 to 3. So let me say what this is called. This is called the closed interval method. Which has 3 steps. So 1, find, or really 2 points, find all critical numbers of f of x. Number 2 is plug in all critical numbers and endpoints to f of x. And then step 3 is the largest result is the absolute maximum. And the smallest result is the absolute minimum. Okay? What identifies this problem to be a closed interval? Because I've told you, well, in this case, it's artificial. I just said we have the interval from minus 2 to 3. That's a closed interval, right? Because it includes the endpoints. What we're going to see with word problems is that sometimes you'll be able to tell from the problem that you're on a closed interval. We'll see how that works. Okay?
Yes. So in
Yes.
the case that August,
Yeah.
so in the case if we have the interval, the closed interval to be 0, so we A B is let me say the point, the critical point to be 0. Will it be a closed interval also?
Yeah, I mean, well, so remember, the closed interval, the critical points are just where the derivative is equal to 0 or where the derivative doesn't exist. So you compute all of those, and you only take the ones that are in the interval. So in this case, maybe this function will have some critical points outside the interval from minus 2 to 3. We don't need to use those because we only care about the interval from minus 2 to 3. So I should say the...
Okay, so
Yep.
that means if we have two positive numbers to be the point, the function or the domain, will it still be a closed interval?
Yeah. So if you had two positive numbers, then if you found a critical point at 0, then you wouldn't use that one. Yeah.
Hello?
Okay.
Hi, Enoch?
Yeah, so if we are giving this type of thing, I want to know if this interval you're giving are negative 2 and positive 3 inclusive. Are they inclusive?
Yes. Oh, sorry. Yes. So the notation, the square bracket means inclusive always.
Okay.
Right?
So yeah.
If we have a round parentheses, that means it's not included. So
Okay,
the
so
square bracket means that it's closed. Yeah.
Yeah. So the first thing, if we like, we can make the table of the function and the value inputted, which means from negative 2 to positive 3, which means we are taking it from negative 2, negative 1, 0, and you are taking 0, 1, 2, 3. on a
Oh,
table
yeah.
value and get it value.
Right. So we can do that, but we don't really have to, right? I mean, so first of all, this is a function on the full interval. So it's not only at the whole number of points, but it's also at all the real numbers in between, right? So wherever this absolute minimum and maximum is, might not be at a whole number, right? I mean, I think in this example it is, but it doesn't have to be that way,
Oh,
right?
okay.
So, I mean, so a table of values can give you a little bit of intuition, but it's not necessary for solving the problem, right? So for something like this, we're going to do step one. We find all the critical numbers. Well, f of x is a polynomial, so it's differentiable. The derivative exists everywhere. So there's not going to be any points where the derivative doesn't exist.
Okay, so so if you like, can you differentiate and insert the value of -2 and 3 as s and y?
Right. No. You don't want to set them as x and y, right? So the endpoints are only going to figure in here in step two, right? We
Oh,
plug in
okay.
all critical numbers and endpoints. So this is where the
Okay.
endpoints are. So when we do step one, all that we do is we want to find the critical numbers. So we just set f prime of x equal to 0 and solve for x,
Oh, okay.
right? We want to see where is this function equal to 0. So James says it's 8 at x equals 1. That seems probably correct, but let's do it out. So what we get with the derivative is we get 6x squared, right? 2x cubed, right? The 3 comes down here. Then here,
Yes,
the 2 comes down here. So minus
6x squared minus
6x
6x minus 12.
minus 12 equals 0. So we can divide out by 6. So that's x squared minus x minus 2 equals 0.
Yeah.
This gives us x minus 2 times x plus 1 equals 0. And
Yeah, so you have 2 and -1.
right, x equals 2 or x equals -1. Great. So that's step one. So these are our critical numbers, right? We have 2 and -1 are the critical numbers. We're setting the derivative equal to 0. This is the key step. This is step one. Is setting the derivative equal to 0 is what you do for these maximum and minimum problems. Okay. So number two, we have to plug in all critical numbers and endpoints. Now, these are both in the interval. The 2 and the -1 are both here. So we have to try both of them. So we're going to have to plug in 2, -1, and then also the endpoints, -2 and 3. So what do we get here? F of 2 is, let's see, 16 minus 12 is 4, minus 24 is minus 20 plus 1. So f of 2, I'm just going to do this in my head. You can check it if you want. So f of 2 is minus 19. F of minus 1 is going to be, we get minus 2, minus 3 is minus 5, and then this is 7, and then plus 1 is 8. Then f of minus 2 is going to be, we get negative 16, and then minus 3 times 4, so that's minus another 12, so that's negative 28. And then the 12x here is going to give us, we're going to add 24, so it's going to be negative 4, and then plus 1, this is going to be minus 3. And then lastly, f of 3 is, that's going to be 54 minus 27 is 27, minus 36 is negative 9, and then plus 1 is equal to minus 8. Okay, so this is what we get when we punch in these numbers. That's step 2. And now step 3 is very easy. We just have to say which is the biggest one, right? Well, here it seems like f of minus 1 equals 8 is the biggest one. And what's the smallest one? Well, f of 2 is going to be negative 19. That looks like it's going to be the smallest one. Did I do that wrong? No, that's right. Okay, so f of 2 is going to be minus 19. Okay. So this is what we have here. Let me just make sure this 16 minus 12 is 4. Yeah, so this is right. Okay, so what this shows us is that the absolute maximum.
Hello?
Yes, hello?
It was almost like what I was saying. Even if you are going to get a table value, you are still going to get those same values.
Right, but we got lucky. I mean, it's because in this example, we found our critical points at integers. But maybe, but we didn't know that was going to happen, right? So it could be that the critical values are not, the critical numbers are not integers, and then you would have missed them in the table of values. So in this example, it works, but you don't know that that works all the time. Okay. So here the absolute maximum is going to be equal to 8, which is achieved at x equals -1, and the absolute minimum is equal to -19, which is achieved at x equals 2. Okay, so this is the solution. Okay, so this is the three-step process. We set f prime of x equal to 0 to find all the critical points. We then punch in all the critical points and the endpoints, right? So let me label that, right? These here are the critical numbers, and these here are the endpoints. Okay, so we just do everything in on equal footing, and then we just look which is the biggest and which is the smallest. And this is telling us that the biggest value is going to be 8, and the smallest value is going to be -19. All right, any questions on that? Okay, great. Okay, so this is kind of basic example of how to do this. So, and the key computational step is setting the derivative equal to 0. That's what you do for all of these optimizations. Okay, so how do we do this in real applications? I mean, here I just gave you some function. I didn't try to connect it to anything in the real world. What do we do when we have an actual application? Oh, sorry, Theophilus, you have a question? Oh, Armstrong, I see. How do we get 2, 1, -1, -2, and 3? So here, 2 and -1 were the critical numbers. They were the solutions for x when we set f prime of x equal to 0. So these were the critical numbers. -2 and 3 are just the endpoints of the interval that I gave you. This is the interval where we're trying to find the maximum and minimum of the function. So that's why the 2 and the -1 here are the critical numbers, and the -2 and the 3 are the endpoints, and so we have to use all of them.
Hello?
Yes, hello, Rash?
Yeah.
Mm-hmm.
So are we going to differentiate Fred before we start to plug in the value, right? To find the
Yes,
critical number.
exactly. We find the critical values, and yeah, maybe I should say, we're plugging these in directly to f, to pure f, the original f. We're not plugging them into the derivative. Because if you plug these into the derivative, you just get 0. What you do is you get a bunch of x values, and then all of those you plug into the original function to find out which is going to be the biggest and which is going to be the smallest.
Okay.
Yeah, you're welcome. Theophilus, do you have a question? Sorry, I'm not getting you. Maybe you can type the question. Okay. Well, so in the meantime, I'll move on and we'll get the question afterward. Okay, so how do we do this as an application? So how do we optimize a quantity in a real life situation? Well, you need to model the situation with math, right? So you have to interpret whatever situation you're in as maximizing or minimizing some function on some domain. And this will often require several steps. So the first step, understand the problem. What are you trying to maximize or minimize? What are the constraints? Number 2, if it's relevant, draw a diagram or introduce notation for the relevant quantities. Number 3, express the quantity Q to be maximized or minimized in terms of the other quantities in the problem. Number 4, maybe Q looks like it's a function of many variables, but we can usually use relations among the input quantities to rewrite the expression for Q so that it's a function of only one variable on the particular domain. And now you have a Q that you want to maximize or minimize. You have a function of one variable on a domain, and now we're in our situation. We know how to take the maximum and the minimum, at least if we're on a closed interval. So now we're going to maximize or minimize the relevant function on the domain. So these are the steps you need to do to compute a word problem or something that you're trying to model into a calculus problem. Okay? And rather than just go over the steps in the abstract, I think it's easier to understand them in the context of an example. Okay, so let's do an example of this. Okay, and so all right, so let's look at an example. So let's say we're going to use 1,200 square centimeters of material to make a box with a square base and an open top. And we want to find the largest possible volume of the box. Okay? So what does it say? Step 1, understand the problem. What is to be maximized or minimized? What are the constraints? Well, in this case, that's pretty clear, right? We want to maximize the volume. And the constraints are we can't make a box as big as we want. The constraint is 1,200 square centimeters of packaging. Okay, so we have what we're trying to do. This is what we're trying to maximize. And now number 2, draw a diagram and introduce notation for the relevant quantities. So this is a problem about a box with a square base and an open top. So I should draw a box with a square base and an open top, right? So this is my box over here with a square base and an open top. Maybe I'll draw it not as a cube, but as something a little bit shorter, just so that we see that this thing is not necessarily supposed to be a cube. Okay, so this is my box. Okay, and it's got a square base and an open top. So this is maybe a diagram. My box with a square base and an open top. Maybe I'll draw it like this. Okay, so there's my box. Okay. Okay. And now what we have to do is label notation for the relevant quantities. So what are our choices? Well, for making a box like this with a square base, well, this side maybe has length S, and it's a square base, so this side has to have length S also, S for side. And then the height of the box, maybe we'll call it H. And the quantity that we want is the volume, and the volume of this box is going to be S times H, or in other words, S squared H. Okay, so this is the quantity. It's going to be S squared H. This is what we want to maximize, right? We want to maximize this. This is our volume to be maximized, right? Okay, I haven't done the problem yet. Seems reasonable, but let's see. So this is our volume to be maximized. Now, what do we have next? We need to use relations among the input quantities to rewrite the expression for Q so that it's a function of one variable, right? We can't do this yet because right here we have S squared H. We've got 2 variables. We don't know how to work with 2 variables yet. We need to work with 1 variable. So, but what does our constraint say? Our constraint says we're using 1,200 square centimeters of material, right? So what does 1,200 square centimeters of material say? Well, how much material do we need to make this box? Well, this box has a bottom. The area of the bottom is S squared, right? S by S, right? This is the bottom. And then it's got 4 sides, and each side is a rectangle with area S times H. So we have to add 4SH. This is going to be 4 sides. And we know that this sum is equal to 1,200.
Yeah,
Yes.
good, sir.
Yes, Prince.
Yeah, you said at the bottom is S square, and we have at the bottom we have X. How can it become S square?
Because the bottom,
Is that because
each
we are looking
side
at
is S.
alpha?
So the box has a square base. So it's S and S. So the
Oh,
bottom is
okay,
S
okay,
squared.
okay, okay,
Yeah.
okay, okay. All the other
Yeah.
sides too. Okay, I didn't see the other side.
Right.
Okay.
And then the four sides is each side is SH. So we get 4
Okay.
SH. Right.
Okay. So another question is, we have four SH. So the four, what do they simplify here? What how it came to become four?
Because it's four sides. 1, 2, 3, 4.
Oh, sure. Very good.
Right. So we've
Thank
got
you.
the box, right? So we have four sides over here. That gives us 4 SH.
Yeah, hello,
Oh,
boss.
Hello. Yes, Enoch?
Yeah, I beg of your indulgence. I want you to please read this question over and again. Let me hear.
Okay, so if 1200 square centimeters of material is to be used to make a box with a square base and an open top, so there's no top, we don't need to use the material on the top, then find the
Okay,
largest possible volume of the box.
okay.
Yeah.
So we are just assuming that this diagram is the 1200 centimeter, right?
Exactly, because this is how much material we have,
Okay.
right? So the point is, we would like to maximize S squared H, but that's two variables. We need to get it in terms of one variable. And what we're going to do is we'll use our constraint for this. Because S squared plus 4SH equals 1200, what we can do here is we can solve for H in terms of S. Solve for H.
Okay, so now you have
terms-
four S8 equal.
Right.
Yeah, so you have 4S8 equal 1200 minus S squared.
Right.
So now it divides both side by 4x, it divides both side by 4x. So you have.
Right. So this is what we get, right? We get S is 1200 minus S squared divided by 4H. Right. So sorry, I didn't do this right. Sorry, solve for H in terms of S. Sorry, H is 1200 minus S squared over 4x.
Yeah.
Yeah, sorry.
Yeah.
There we go.
Yeah.
Thank you.
This is what I just asked.
Yeah. Okay, so this is what we have. And so now that we've written H in terms of S, now we can write that Q is equal to S
Yeah.
squared times.
Yes,
Yes, Enoch?
finish. What are you doing first?
Okay, so it's S squared times 1200 minus S squared divided by 4S. And this simplifies to S times 1200 minus S squared over 4. Or if we want to keep simplifying, this becomes 300S minus S cubed divided by 4. Right? Because this here is H. So we end up getting that the volume that we want to maximize, maybe instead of calling it Q, I'll call it V for volume. And so this volume over here, which we'll call V for volume, in terms of how big we're going to make the sides of the box, that it can be written as 300 times the length of a side minus the cube of the length of the side divided by 4. Yes, Enoch, question?
No, it's the same question I wanted to ask. You are already solving to insert the value of H and simplify the fraction into separate parts. You
Okay.
are already done it.
Okay, good. So,
Okay.
so yeah, so now, and what's our interval, right? What's our interval? Well, we know that S is greater than 0, right? Or it has to be at least 0, right? Because you can't have a negative side length. And we also know that S, well, if we're going to use 1200 square centimeters, then S can't be any bigger than the square root of 1200, because otherwise you're using more than 1200 for the bottom of the box already. So S is definitely going to have to be less than the square root of 1200. So now we've basically converted this into a closed interval problem. So now what is the point? We want to maximize 300S minus S cubed over 4 on the interval from 0 to square root of 1200. Okay, so S is less than square root of 1200, otherwise not enough material to make the bottom.
Square root.
Hello?
Yes, question, Rush?
All right. You can still simplify in a way that the factoring was what we have, it can still be that 20 to the root of 32, right? 0, comma 20 to the root of 32, right?
Yeah, that'd be fine. But yeah, either way is fine. That's fine, but it's not necessary. Okay. So now we took this problem up here that really did not had one number, mostly its words, and we've converted it to a maximization problem of the old type, right? Maximize a function on a closed interval. So now we can take care of this using the closed interval method. We're going to find the critical points and we're going to try the endpoints. Okay, we're going to go try the endpoints.
Yeah, that boss.
Yes, Enoch?
Yeah, the interval. What did you read it so big or 1200? What if I want to read it 20 root 3?
That's fine. It makes no difference either way.
Okay, what if I just want to say 0, 20 root 3?
Yeah, that's fine too.
Okay.
Yeah, it doesn't make any difference. Yeah, if you want to say 20 root 3, that's perfectly fine. Okay, so let's see what happens. So now we want to maximize this. So I'm going to just repeat this. We'll need a new page. We'll need a new page. So it'll probably be one example short today. So new page, let me just rewrite what we're trying to do. We're trying to maximize, what is it? 300s minus s cubed over 4 on the interval from 0, let's say, to 20 root 3.
Hello?
Okay. Yes, hello, Rash?
Is this the 0, comma 20 root 3 is the critical numbers or what?
No. These are the endpoints of the interval. No, we haven't found the critical numbers yet, right? The 0 to 20 root 3 is just what can s be? S is a side of this box. It certainly can't be any lower than 0, right? Because it's the side of a box. It can't be a negative number. And it can't be any bigger than the square root of 1200 because once it gets bigger than the square root of 1200, you don't have enough material to make the bottom because you only have 1200 centimeters squared of material. So the biggest it can be is square root of 1200 by square root of 1200. That would use 1200. So that's the maximum that it could possibly be. And the minimum that it could possibly be is 0. So you're working on this closed interval from 0 to square root of 1200. Again, if you care, this is kind of not at all what's important in the problem, but you could write square root of 1200 as square root of 400 times square root of 3, and that's 20 root 3. But this simplification of the radical is not important, okay? It's not what's important about this problem. Okay, you can just write it either way. It really makes no difference at all. So I wrote it originally as square root of 1200 because that's what's easy to see, that's the biggest that the box can be, right? Because square root of 1200, square root of 1200 gives you 1200, and you can't make the box any bigger because you don't have enough material to do that. Okay? So let's go here. So we're maximizing this on this interval. So now we do our closed interval method. Remember, our closed interval method has 3 steps. So 1, we need to find the critical points. And the way we do that is we set the derivative equal to 0. So we want to set the derivative equal to 0. So taking the derivative here, we get 300.
Yeah, so yeah,
Can I just do this? Let me just do this myself, okay? Just because I want to get through it, okay? So we have 300. So we take the derivative here. We get 300 minus, and then we're going to get 3s squared divided by 4 equals 0. And that's going to be the same thing as 300 equals 3s squared divided by 4. And that's 1200 equals 3s squared. And that's going to give us that 400 equals s squared. And this gives us, this is important, 20 equals s. And it's not plus or minus 20. It's only 20 because this is our side. It has to be in this interval. It can't be a negative number. Side lengths are not negative numbers. So we're only going to take the positive square root here. So we have only side length equals 20, right? Now what we have to do is plug in S equals, well, our endpoints, 0 and 20 square root of 3, and then also the side length equals 20, right? So what happens when we do this at 0? So at S equals 0, this gives us that the volume is 0, right? I mean, we plug it in here, this gives us 0 when we plug in S equals 0. Okay, so we'll plug in this, I'll say, to V equals 300S minus S cubed over 4. Okay. So S equals 0. This gives us V equals 0. And then, so what about S equals 20 times square root of 3? This gives us V equals 600 times square root of 3 minus what's S cubed divided by, oh, sorry, it's 6,000 square root of 3. And then minus S cubed is going to be 8,000 times square root of 3 cubed over 4. And this turns out this is just 6,000 square root of 3 minus the 8,000 over 4 is 2,000, and square root of 3 cubed is 3 root 3. So this is going to actually simplify to 6,000 root 3 also, which is going to give us 0, which it makes sense because at 20 root 3, you're using all the material for the bottom of the box, so there's no volume because you don't have anything left for the sides. And then you've got the actual one, which is going to be the right answer, S equals 20. This gives us that V is equal to 300 times 20 minus 20 cubed over 4. And this turns out to be, so that's 6,000 minus 8,000 over 4. And this turns out to be 4,000, and our unit here is cubic centimeters. Okay. So this turns out to be the maximum volume. All right. So the maximum volume, this is step 3, is finding the maximum volume over here. Maybe let me see if I can get this. That this should be better. Okay, it's a little bit easier to see now. Okay, so just going back here, we had to first do a bunch of modeling. So these problems are multi-step problems. They're intense problems, and there's lots of places to make a mistake. Okay, so James's answer was correct at the beginning. That's great. It was the 4,000. So you have to draw a diagram. You've got to write a formula for what you want to maximize. You have a constraint. If your formula involves 2 variables, then your constraint is going to help you solve for one variable in terms of the other. And that will allow you to convert your formula into a formula only involving one variable. So we have our 300s minus s cubed over 4 on some interval. Once you've done the conversion into math, then what you're doing is a standard closed interval optimization. So you now have just a function that you're trying to maximize on a certain interval. And for that, you can use this closed interval method. Find the critical points and then plug in the different values, plug in the endpoints and the critical points, and you see which one gives you what you want. Clearly here, volume 0 is not what you want. Over here, volume 0 is not what you want. But when you plug in 20, this is what you want. So the biggest box you can make is going to be 4,000 cubic centimeters. Okay,
Hello?
questions? Yes, Rash?
From the starting point, man, I saw a formula there. I seen, just go back to the first.
Yeah.
Okay. I seen s squared plus 4s h equals to 1,000. Is that a formula to using or what? Is that formula inclusive?
Yeah, I mean, it's just we're talking about what is this? It's really the surface area of the box, right? So the box has 5 parts. It has a bottom and it has 4 sides. So the s squared represents the bottom of the box, and each side is a rectangle, right? So it's sh, and there's going to be 4 sides. So it takes 4 sh amount of material to make the 4 sides.
Thank you.
So the total amount of material you have is 1,200, so they have to be equal.
Thank you.
All right, you're welcome. Other questions? Okay, so I think we'll have time for one more example. So let me, there's two more examples in the notes, but we'll only have time for one of them, okay? So let me just say, sometimes an optimization will naturally take place on an open interval rather than on a closed interval. So in this case, we can use the following results. So if you have a critical number for f of x, so maybe this will be easier if I draw it, right? Let's say that I have a critical number c over here. Well, if the derivative is positive for all x that are less than c, and it's negative for all x that are greater than c, then f of c is the absolute maximum value. So what that means, the way we draw this would be, let's say that we have our value f. So f of x is going to be positive for all x that are less than c. So that means it's increasing. It's sloping upward up to c. And then if f prime of x is negative for all x that are greater than c, that means when you get past c, the slope starts to go downward. Then what that tells us is that over here at c, you're going to have the absolute maximum. And the second part of this theorem is just the opposite, right? If we have some c here, some critical number, and this is our point here, and if we have that f of x is less than 0 for x less than c, so it's decreasing down to c, the rate of change is negative, and then f of x is greater than 0 for all x greater than c, so it's increasing from c, it's going to be something positive, right? Then what we see here is that f of c is going to be the absolute minimum value of c. So this is the absolute minimum here. Okay. Okay, so we got the absolute maximum and we've got the absolute minimum over here. So in order to find the absolute maximum or minimum, if we know there's only one critical number and we have that the value of the derivative is negative on one side and positive on the other side, then this guarantees us that we have the absolute maximum or minimum. And what's nice about these open interval problems is that we don't even need to check the endpoints. Okay, if you have only one thing like this, then it's going to be the absolute minimum or the absolute maximum. Okay, and so in order to find it, it's enough to just find the local extremum, and this is what happens. This is going to be at the critical number. Okay, so let's just see one example of this, and then we'll have to go by. So then we'll have to move on. Let's see which one. Okay, let's actually, I'm gonna skip the, no. Let's do this example. Example 3 we can leave as homework, okay? So suppose that we have a cost function is the cost of producing X units of a product. It's gonna be 16,000 plus 200X plus 4X to the 3 halves. And so we wanna know how much product has to be produced to minimize the average cost of production. And what is the average cost of production in this case? So what we see here is the average cost is going to be the cost function, that's the total cost, divided by the number of items, right? So it's C of X over X. This is the total cost, and this is the number of items. Okay. And so the average cost in our case, this is going to be 16,000 divided by X plus 200 plus 4X to the 1/2. Right? All that I did was take my C of X and I divided each term by X. Okay. So to minimize, and where does X live? Well, X here is going to be in the open interval from 0 to infinity, right? We don't know. There's no maximum on how much we can produce. And if we produce zero, then it doesn't even make sense to talk about the average cost because you can't divide by zero.
Yeah.
So we're really working on
Yeah,
an open interval here. Yes, yes, Prince?
yeah, Prashad.
Yeah.
We have 200x plus 4x raised to the k power over 2. And here we have you wrote 200 plus 4x raised to the
Right, because this is C of x. This is the total cost function. The average cost you have to divide by the number of items. So I'm dividing each term by x, right? So maybe I'll add one more step. What is this really? This is 16,000 plus 200x plus 4x to the 3 halves, all divided by x. And then term by term, we get this. That's 16,000 over x plus 200, and then plus 4x to the 3 halves over x, which is 4x to the 1 half. Right? Each individual term is getting divided by x.
Oh, okay.
Right.
Okay.
Okay.
Let's go to.
Okay, good. Okay, so since we're low on time, let me just do this. So what we're going to do is find the critical value, or find the critical number. So we're going to set the derivative equal to 0. Equal to 0. And so this gives us, remember, what do we have? 16,000 over x is the same as 16,000 x to the minus 1 plus 200 plus 4x to the 1 half. The derivative.
So you have minus 16,000 over x squared.
Yeah, so minus 16,000 x to the minus 2
plus
0,
2,
right?
2 over square root x.
Right, so plus 2x to the minus 1 half. So what this gives us is 16,000 x to the minus 2, yes, equals 2x to the 1, yes?
It's
So I want to
only
set
minus
this equal to 0.
the power.
Yeah, sorry, 2x to the minus 1 half, thank you. Okay, so this has to be equal to 2x to the minus 1 half, and so this is 8,000 x to the minus 2 equals x to the minus 1 half, and if we multiply both sides by x squared, so times x squared and times x squared, we get that 8,000 equals x to the 3 halves. And so inverting the power, we get that 8,000 to the 2/3 is equal to x. And if you calculate this, you get that x equals 400. So I had to do that fast because we're running out of time, but x in this case is going to be equal to 400. And it's the only critical point. What's going to happen here, I don't really have time to check this, but the hypotheses of the earlier of this theorem over here are going to be held. So what that means is that this derivative is going to be negative for all x values that are less than 400, and it's going to be positive for all x values that are greater than 400. Maybe next time we'll go over this a little bit slower because I have to rush this, unfortunately, because I need to finish up. But basically what we have is that this x is equal to 400, and then the average cost is just going to be, we plug in 400 over here. So let me just do this on another sheet. So the average cost is, what was it, 16,000 plus 200 times 400, and then plus 4 times 400 to the 3 halves divided by 400. And this is going to be, well, 16,000 divided by 400 is 40. And then 200 times 400 divided by 400 is 200. And then 4 times 400 to the 3 halves divided by 400 is 4 times 400 to the 1 half. And this is equal to 40 plus 200 plus 4 times 20. And that's going to come out to 320. So this is going to be the average cost per unit. Okay. So I assume this probably went a little bit too fast for everybody, and unfortunately, I really do have to get going, so I don't have time to go over this. But next time when we pick up, we will do some more optimization problems, and we'll maybe start by going over this one a little bit slower so that it makes sense. There's another problem here. I'll leave this as an exercise. So find two positive numbers whose product is 100 and whose sum is minimum. Think about how you could set this up. And then there's lots more exercises to do. So you have a whole month. So you have time to do a bunch of exercises. So number one is find the absolute minimum of this function on the interval from 0 to 3. Yeah, James, so that's right. 320 was right. 2, the sum of two positive numbers is 16. What's the smallest possible value of the sum of their squares? 3 is a little bit more complicated. A fence 8 feet tall runs parallel to a tall building at a distance 4 feet from the building. What is the length of the shortest ladder that will reach from the ground over the fence to the wall of the building? You're going to have to draw some pictures and use some trigonometry here. And then 4, a business example. So Joseph makes and sells necklaces at the beach. Last summer, they cost 150 Liberian dollars each, and 20 were sold each day. When he increased the price by $10, he found the average decrease by 2 sales per day. Assuming a linear relation between price and quantity, what's the function f of x giving the number of necklaces sold as a function of price? What should Joseph set the price of a necklace at to maximize his total revenue? Okay, so all of these, we'll go over them nice and slowly next time. I'll send them out, but you have a full month to think about them, and you can ask questions over the chat if you want. And so just as a reminder that we have a holiday break for the next month, and we'll resume class Thursday, January 23rd. And so I will say,
Hello.
Yes, hello.
Yeah, it's Enoch. I want to know
Yes.
there's all of whom were SSI. When do you?
Whenever, just before our next class, you have the whole month.
Oh, okay. Thanks a lot. Thanks.
All right. You're welcome.
I ain't got it there, man.
So I apologize on this example for having to go a little bit fast. We're going to spend another class on optimization because it's very important. I want to make sure that I do it thoroughly and clearly. So we'll spend another class on this, and I'm sure after a month people will forget things. So we'll spend time going over all of these examples nice and slowly for one more class before we move on. Okay, so thank you as always for showing up. And I guess I'll stop the recording now.